Hello, everyone. Thanks for the introduction. My name is Zhou Fan. I'm currently a PhD student at Harvard. And today I'm going to talk about our paper, Optimal Automated Market Makers, Differentiable Economics and Strong Duality. This is a joint work with Michael Curry and David Parks. I think Michael is also sitting there in the audience. So when talking about the design of automated market makers or market makers in general, there can be different design objectives to maximize for. Some designers might want to, their top priority might be to maximizing liquidity instead of maximizing profit. But for the scope of this paper, we are focused on profit maximizing market makers. And the principle behind the profit for a market maker is very straightforward. You buy low and sell high. The market maker has their own belief of the fair values of the traded assets, and they're willing to sell those assets at prices higher than the estimated fair values. And similarly, they are willing to buy at prices lower than the fair values. And if they do this right, they can, by offering trades on both directions, they can capture the price difference as a profit. So in an ideal scenario for the market makers, when their estimation of the fair prices are accurate, this is pretty straightforward. But in the real world, the asset prices would fluctuate constantly as new information enters the market. And if the trader is better informed than the market maker could incur a loss. For example, here, we have this market maker valuing the apple at 55 cents. And if a trader comes to the market and says, I'm willing to buy the apple from you at 60 cents, this looks like a good trade for the market maker because theoretically they make a profit of 5 cents. But as a market maker, we also need to ask the very basic question, why does this trader want to buy this apple, or why is the trader willing to take the higher price than our estimated fair value? One possibility is that they just want to get this liquidity, and that's great for us because we just provide liquidity to capture the premium price difference. But another possibility is that the trader might have some private information that suggests the fair value of an apple is now actually higher than 60 cents, maybe 80 cents. And if that is the case, it's really bad for the market maker because we actually are losing money by providing this trade. So it's very crucial to take into consideration adverse selection when designing market making strategies. And this is especially the case for DeFi because in DeFi, automated market makers are deployed as smart contracts running on-chain. And a lot of things can happen off-chain. And new information typically come off-chain, like price discovery typically happens first at centralized exchanges. And when things happen, price change on centralized exchanges, there could be a difference between that new price versus the price that you are providing in your smart contract. And arbitrageurs will come in, and that is exactly adverse selection. And that's why people talk about impermanent loss or divergence loss in DeFi. And Milionis et al. Wrote a paper in 2022. They studied a rich space of market-making strategies for between one asset and the numeraire. And within this one-dimensional market-making strategy design space, they also consider a specific model of adverse selection. And by searching through this rich space of strategies, the result is that in one-dimensional case, or just between one asset and numeraire, the optimal market-making strategy is pretty simple. You just provide a bid-ask spread. That is, you offer one buying price and one selling price. This also aligns with the traditional finance space. So in addition to making market between two assets or one asset versus a numeraire, it's also common to have markets across multiple assets. That is, at least 3 assets, including the numerator. And with the existence of more assets, the design space is even richer. There are examples of designs that allow trades across a bundle of multiple tokens, both in traditional finance and also in DeFi. In traditional finance, the examples would be One Chronos, TradeWeb, and also the flow trading model proposed by Budish et al. And in DeFi, the example would be the multi-token AMM pools. And so if we want to do the market making strategy design for multiple tokens, what can we do? The simplest or the most straightforward solution is you just have a one-dimensional market making strategy for each of those traded assets, and you just combine them together, and that's your very straightforward strategy. That's the figure on the right. But we want to ask the very first basic question: is this optimal in maximizing the market maker strategy? Or if we can, obviously we can consider more complicated strategies, like we can offer different prices for different bundles of tokens when there are multiple assets. But do we actually need to do that? So that's the first question we want to answer. And to study this problem, we generalized the model from Milionis et al., and we focus on the version with multiple assets. So in this framework, the market maker has their own belief of the fair values of all the traded assets. This is represented by a vector C. And also the trader has their own private estimation of the fair values as well, represented by a vector X. And this trader type X is sampled from a population or a distribution Fx. And so how do market makers provide liquidity? Typically, this is done by offering a menu of valid trades. And when the trader comes into the market, they have their own value X, and they would just pick one trade from the provided menu that maximizes their own utility. Like this is by providing a bid-ask spread. That's basically you providing 3 options. You can buy at that price, you can sell at that price, or you can you can just choose to not trade at all. And this is also the case in constant function market makers. If you think about CFMM curve like Uniswap, and suppose you are currently at some specific reserve state along the curve, then basically you can choose to jump to any other state on the curve, and that is a valid trade. So you're still, when you are just considering the next trade, you're choosing from a menu, and you will, if you're rational, you will choose the one trade that maximizes your utility. So given the market making mechanism or a menu of trades, there is a direct mapping from a trader value X to the trade. And how do we describe a trade? It comes in 2 parts. First, there is an allocation, AX, which specifies the trade quantities or the quantities of each of the traded assets that's transferred between the trader and the market maker. Like each dimension can be either positive or negative, depending on whether the market maker is buying or selling each of the traded assets. And also there is a net payment, PX, that's paid by the trader to the market maker in the units of the numerator. And as I mentioned earlier, we want to maximize the expected profit of the market maker. And this is just this expression. And to take into consideration of adverse selection, we want the market maker to anticipate the degree of adverse selection and then update their belief after every trade according to something called a belief update function, which is represented by the pi xc here. If you think, as the market maker, if you think the trader has some information you would want to move your estimation C a little bit toward their direction. And another thing I want to mention is that there is also this notion called trader utility function. So it's basically just, you can derive the trader utility function very simply based on the allocation and the payment. And I want to note this because this is a very useful thing in mechanism design if we can consider a mechanism in the form of utility function. And when we talk about the revenue of the market maker, this expression, we can express it also in the form of the utility function, because the allocation function can be represented as a derivative of the trader utility, and the payment is also can be represented in the form of UX. So how do we try to solve this problem? So our approach comes in two parts. First, we generalize strong duality tools from mechanism design to take conjectured mechanisms and try to prove their optimality. This is on the theoretical side. And on the other hand, how do we come up with those conjectures that we think are likely optimal? We use differentiable economics approaches or machine learning methods to generate those hypotheses of optimal mechanisms. And our main result is that we were able to prove the optimality of a family of market-making strategies under adverse selection, which shows the behavior of offering mixed bundles. And in addition, we also show conjectures for different settings that has different interesting behaviors. So at a high level, I'll quickly go through the theoretical part. So as I said, we generalized tools from the traditional mechanism design literature. And so on the bottom, on the left side, that's how we can write the optimization objective or the market maker's revenue in the form of the trader utility function U. And this can actually be converted to a dual problem, which is a relaxed optimal transport. And given the way that we use this duality is that given a conjectured optimal market-making strategy, we want to come up with a corresponding dual solution for the optimal transport problem. And if the dual objective matches with the primal objective, we know that the conjectured mechanism has to be optimal. But it's actually very difficult to just try to solve the dual problem from scratch. So, and it will make it much easier if we have a conjecture of the optimal problem, optimal market-making strategy. So how do we come up with that good conjecture in the first place? We can first start about thinking what the simplest strategy look like. That is just by offering a one-dimensional market-making mechanism in each traded asset separately. When there are 3 assets in total or 2 traded assets plus a numeraire, we have one item is the apple and the other is the orange. We offer 2 separate bid-ask spreads for each of those and then combine together. So this 3 plots would be the visualization of this simple market-making mechanism. In the plot on the figure on the left is the allocation function for the first item. The middle one is the allocation for the second item, and the third one is the payment function. For each of those 3 figures, the x-axis is the value, is the trader's valuation of item 1, and the y-axis is the trader's valuation of item 2. So in a one-dimensional case, by providing a bid-ask spread, there is basically something called a no-trade interval that for traders with values within that interval, the market maker is not willing to trade. That's to protect the market maker against adverse selection. And in 2-dimensional case, we also have this 2-dimensional no-trade region, which is a square. And so this is a simple strategy, but we can imagine there are much more complicated designs in this search space as well. But how do we search for those? So we use a neural network, and specifically we model a method called RocheNet. Its basic idea is to use Roche's characterization of truthful mechanisms that truthful mechanisms correspond with convex utility functions. And if we can represent the convex functions as maximization over lots of linear functions, and we can parameterize those linear functions using neural network and optimize that neural networks directly. Therefore, we can optimize for the mechanism. And these are some examples that shows interesting behavior for the conjectured optimal market making strategy and the different settings. And we can go beyond 3 items. This is an example for the mechanism conjectured for 3 goods plus a numeraire. And in addition to just the conjectures, we were able to prove the optimality for one case where the trader distribution is a uniform distribution. And under this linear adverse selection model, we used differentiable economics to generate those conjectures, and we used strong duality to show its optimality. And the main takeaways is that, so the first basic question, offering one-dimensional market makers for each different asset separately is not enough to maximize the market makers' utility. And it makes sense to do mixed bundling for market making across multiple assets. And a very interesting aspect of this work is that we use computational tools. We just train randomly initialized neural networks to generate the interesting conjectures for optimal AMMs. And also another takeaway is that there is a rich literature in mechanism design, and more of them can be adapted to the space of DeFi.